want to talk to you a bit about what's known as relative density or specific density, right? So what relative density is an object's or substance's density relative to water. So relative density is actually the density of the substance divided by density of water. Okay, now the density of water is 1,000 kilograms per meter cubed. Okay, and what we can say here is that if the density of let's say gold is 1932 kilograms per meter cubed, you divide it by the density of water, which is 1,000 kilograms per meter cubed, and you get what is known as the relative density of gold, which we can see in this table here, which would be roughly 19.3 or 19.32. Okay, so relative density is how many times bigger you are than water. If you're a decimal like 0.7, you'd be 70% of what water has. Likewise, same thing for lead. If I want the relative density of lead, I can get 11,000 and 342 kilograms per cubic meter divided by 1,000, and you can see roughly we're expecting roughly 11.35, but apparently it's 11.34 according to this calculation. So there you go. So that's how you get relative density. Okay, now if I said a substance has a relative density S, then its actual density is 1,000 times S. So whatever your relative density is, whatever your substance density is, its relative density times the density of water. See, if I cross multiply up here, so we can say the density of substance equals relative density multiplied by density of water, which we all know is 1,000 kilograms per meters cubed. So we're going to use this type of question on floatation questions in exercise 13A, questions 5 and 6. I'm first going to guide you through the a sample question first, okay? So the first thing we have is a cylinder radius r and height h has relative density S. So the substance the cylinder is made of has a relative density S. Okay, so this means its rho, which is its actual density. So rho is the symbol for density, rho material. So the actual density of the material is going to be 1,000 S. Okay, so that's the first thing we know. It's floating in water where it acts as vertical. Great. It's then depressed vertically, so it means you get pushed down vertically so that more of the cylinder is underwater. Okay, as we can see in the second question. So currently at the very beginning, your weight acting downwards versus your buoyancy force acting upwards is balanced. So your net force is 0 because it's not in motion, okay? But when you push the cylinder further underwater, its buoyancy force becomes larger. Okay, so you have the original buoyancy force here, but then you also have an extra buoyancy force P dash battling your weight. So when you release this system, it should bob back upwards, okay? So that's what we're looking at so far. Okay, we got to show that this will perform similar harmonic motion and find an expression for the period of time. So when the cylinder floats in equilibrium, its weight W must equal its buoyancy B. Done. We will take downward pressure in the positive direction. Okay, so downwards is positive. Okay, when the cylinder is depressed downwards a further distance x, so we're calling the distance you push it underwater. So we're going to push, so if you imagine this little distance x above the water in scenario 1, it's going to be below the water in scenario 2, where we push the cylinder underwater. Okay, and then we go, there's an extra buoyant force P dash, which is called in play. This buoyancy force is in upward direction and therefore negative. So because the extra buoyancy force is upwards, we're considering this up is negative, down is positive. Okay, and therefore negative is equal to the weight of the extra water displaced. Now, this formula here is basically the volume of water you displace This is Archimedes' principle. So the volume of water you displace is equal, the weight of the water you displace is equal to the upward force. So the buoyancy force equals weight of water displaced. Now, what is weight of water displaced? Well, it's going to be your mass times gravity. But how do you calculate mass? Well, density equals mass over volume, and density has the symbol rho in this question. So therefore, M equals rho V. So this is going to be rho V, or V, volume of the water displaced, rho and G. Now remember, the volume of the water displaced is equal to the volume of the object submerged in the water, and the extra buoyancy is going to be the B dash is going to be determined by the volume of this little black area here, because that's the extra volume that you have now submerged under the water. Okay, so that is pretty much what we need to know. Now it's a minus because the buoyancy is acting in the opposite direction, okay? But you don't really need to worry about that too much, okay guys? Next thing we're going to do is we're going to run you through the solution that's in the book and see what we can make of it, okay? So the first thing we're going to do here, guys, is we know it's a cylinder, so it's extra buoyancy force. It's a cylinder of height x. Okay, so if you imagine this, the extra water that's displaced is basically like this, and this is the extra bit of the cylinder that's now underwater. It has a height x and it still has a radius r. So minus its volume, which is going to be pi r squared x, because it's a cylinder. Okay, and this is, remember, it's the amount of water displaced, so it has to be times 1,000 is the density of water. Okay, and then you have your gravity there. Okay, so that is your extra buoyancy force, done and dusted already. Next we're going to do is find the mass of the whole cylinder. Now the mass of the whole cylinder is going to be its volume times its density. Volume times density. Okay, now its volume is pi r squared h, because that's the entire h. Now what about its density? Well, we know its relative density is s. So instead of using 1,000, we're going to use 1,000 s. If this was, let's say, if the material was gold, or what do we say here? The gold was 19.3. If the material was gold, s would be 19.3, and this would be 19,300. But we don't know that. Okay, so what we're finding out now is the mass of the entire cylinder. And the mass of the entire cylinder will now be 1,000 pi r squared hs. Okay, next thing we got to realize is that because in scenario 2 there is basically extra force. So there's extra force acting upwards. The net force is going to be acting upwards, okay? So we can get is F equals ma. But the extra force is all due to the extra buoyancy. Because remember, B and W, the initial B and the initial W, they are in complete balance with each other. So there's only one force acting upwards, and it is the extra buoyancy B dash. Okay, so basically what we have is B dash equals ma, and then we can get our two answers here. So remember, mass is this one here, so it's going to be the mass of the object, which is the mass of the entire cylinder, which is 1,000 pi r squared hs. Okay, and then the B dash, which we had up here, minus 1,000 pi r squared x. See that? 1,000 g pi r squared x minus pi r squared x. 1000g. Now, what can cancel off both sides? And then that we have the mass, and then we have the acceleration there. So the thousands cancel, the pi r squareds cancel, and then we're left with, we want to get a on its own. So a is going to equal minus g over hs. Okay, and this, since the acceleration is proportional, so we'll get this here. So this is why it undergoes simple harmonic motion. Since the acceleration is proportional to x and in the opposite direction, the cylinder will be formed simple harmonic motion. We also forgot the x there. See the x? It's minus gx over hs. So a is proportional to x, but then because of the minus, it's in different directions to each other. Okay. Now, the next thing we have to do is find the periodic time. Or what does it want me to find again? Let's go back to the top. Show that A will perform similar motion and find an expression for the periodic time. Alright, the periodic time is just 2 pi over omega. Oh yeah. Periodic time is 2 pi over omega. This means we have to figure out what omega is. But what we know already is that A equals minus w squared x, or omega squared x. So it's minus omega squared x equals A. This implies omega squared equals g over hs, which gives us that omega equals square root of g over hs. Okay, so now we got 2 pi. Now you can turn it upside down here, and you can say that 1 over omega would be this upside down, which would be hs over g. So now we can say that the periodic time is going to be 2 pi. Remember, it's going to be 2 pi times 1 over omega, because we want the inverse of it, so it's going to be square root of hs over g. And that is the periodic time, and that is that question done.